Hi, and welcome to Geeks for Geeks. Today, we would be discussing the problem sum of k smallest element in a BST, which is binary search tree. So, before moving forward to this problem, let us first understand what is binary search tree. So, binary search tree is basically a tree. Suppose there is a root node, okay, and this is the left child, this is the right child. So this left child would be smaller than, so I would just write smaller than the root, and the right side would be greater than the root. Okay. And this would be true. This parent child relationship would be true for all the given nodes. Okay. So if this is being respected, that the left child is smaller and the right child is greater, then yes, this is a binary search tree and this should be valid for each and every node. Now let's move back to the problem. So in this problem, we are given a binary search tree and we need to find the sum of all the elements smaller than or equal to the kth smallest element. So suppose we are given 1, 2, 3, 4, 5. The elements are this. And we are told that we need to find the sum of elements less than equal to the third element, that is, the value of k is equals to 3. Then what we would be doing is the first smallest element, this is the second smallest element, this is the third smallest element. Less than or equal to, the answer would be nothing but 1 plus 2 plus 3 itself, which is equal to the value 6. Now let us evaluate the sample test case. So the smallest value here is 4. So this would be counted, okay, because this is less than 3. The next smallest value is equals to 8, which is less than 3. So 2 is less than 3 still, so that is 2. So now the next smallest element is 10. Okay, so we would write 10. And then if we move forward, that is we go to 12, then it is the fourth smallest element and it is greater than. This condition is not true. Less than or equal to. That is why we would have 4 plus 8 plus 10, which is equals to 18 plus 4, that is 22. That is why the output to this is equals to 22. Let us evaluate one more test case so that we would be more clear. So in this test case, I would be listing out all the nodes in their sorted form. So what I would be doing is I would be having 4, I would be having 5, and I would be having 7 and 8, then 10, then 11. So if you see, if I want the second one, what I can do is I can take out the first two, which is equals to 9. So by evaluating two sample test cases only, or if you give yourself some more test cases, you would come to the conclusion that at first we were trying to find which is the first smallest, and then we were excluding it, and then we were again finding the minimum. Then we are again excluding it, then we are again trying to find the minimum. At each point, we need to find the minimum of static elements, that is, the value of the elements are not changing. So if the value of the elements are not changing, then what we do is we can just write all the elements in the sorted form. So the first brute force approach would be finding the smallest element at each point after excluding the last smallest one. So what would be the time complexity of this approach? So for finding the smallest element in an BST, what you would be doing is you would be traversing whole of the BST. That would be big O of n being the number of nodes for each minimum. So for each minimum, we would be doing an operation. In the worst scenario, k's value can be the value n. That is, we need to have all the elements. So it would be nothing but big O of n multiplied by big O of n, which is equals to big O of n square. So this is a n square approach. So can we improve over this? Yes, we can improve over this by using this technique that we were discussing in the drawing. What we can do is we can enlist all the values and then we can sort it. So first we would keep all the values. So taking out all the values would be big O of n itself. And then we would be sorting it. That would be n log n. Okay. And then we would be again traversing it. And then we would be finding the small, that is again, in the worst scenario, it would be big O of n. The upper bound would be n log n itself. Okay. So now can we do better than this or not? Yes, we can do better than this. So if you see that in this question, I would just give you the idea why this is okay. Like what would be the intuition that I would be able to improve over this point? Okay. The intuition is much more important over this. If you see that yes, I am getting the n log n approach, but what is the intuition that in which direction I can move forward? This is the most crucial part here. So the intuition is that if we were to sort the elements, first take out the elements and then we were to sort the elements, then we could have been given any type of tree. But we are given a binary search tree. So this is a clear indication that we need to use the properties of binary search tree. Yes, we can take use of the properties of binary search tree, provided that we know that in order traversal, in order traversal of BST gives sorted output. Okay. So if we do the in order traversal, which is visiting the left part first and then the root and then the right part. If we do this, then we can say that yes, we would get the output in a sorted form. So I would just give you an example. Like suppose we have 1 and this is 2 and this is 3. Here the value on the right side is greater, left side is smaller. So if we do the in order traversal, that would be first left, then root, then right. That would be 1, 2, and 3. So yes, this is working for this, but what about when we have more number of nodes? It is very suspicious to think that in will it work for all scenarios or not? So let us go back. Okay, let us just take a few examples. Okay, just let us do in order traversal for this given one. Okay, so what we would be doing is we would passing this term. So before this term, the root should be visited. We would be coming here. So before this 5, the root should be visited. So left, so 4. So now at this point, there is no left of 4. 4 is after the left of 4 is visited, that is null. So null is already done. Then we go to root. Root is now what? Root is 4. So we would have 4 at this point. Okay. Then we go back because the left of 5 is now visited. So now we need to visit 5. That is after left, we should, so I will be writing here left, root, and then right. So if you, I would just sum up again, the left of 4 is done. So now we would be the chance of root here. The root is 4. 4 is visited. Now 5's left is done. After that, what should be there? Root. That is 5 itself. So we would have 5 here. So the left and the root is done. So we would go to the right part. Okay. So we would go to the right part. Right's left should be visited first. So right's left is not there. So it is now visited. We won't be adding it because that is not present. After that, the root itself. So 7 itself should be visited. And then the right part of 7, which is equal to 8. So 8's left is not there. That is, we would be moving forward with this value only. Then after the left and right of 8 is visited, we would be coming back again. Okay. Then 7 is already visited. The left is visited. Now the right is visited. This work is complete. Now we would go back to 5 again. 5's left is visited. Itself is visited. The right side is visited. So we would be coming back again and we would be traversing up. At this point, the left side is done. After the left side is done, we would be moving forward with the 10. So yes, 10 would be there. Then we have the right side. That is why we will have 11. So if you do the in order traversal of a BST, you would be getting the output in a sorted form. Okay. So how can we solve this problem? So solving this problem is now much easier. Okay. What we can do is we can directly insert the elements in a vector or a list in Java, and then we can take out the first key elements of that. Okay. And what would be the time complexity? The time complexity would be doing an in order traversal, that is big O of n. First one, in order traversal big O of n. And then visiting the k element, that is again big O of n. So time complexity is big often. Talking about the space complexity, in the worst scenario, k's value can be equal to the value n. So we need to take all the elements. So we need to keep all the elements in an auxiliary data structure that is again big O of n. So can we improve over this or not? Okay, yes, we can improve. The indication that we want only the sum, the indication that we want only the sum gives us a proper hint that yes, that means the element is not required. The resultant value is required. So let us try focusing more on the result part. How can we directly get the result without having the elements individually? Like I am not interested in getting 4, 5 and 1 individually. Rather, I can just have the sum and I am happy enough. I can think of this scenario. So now what we can do is we can just do a in order traversal and the first k elements would be contributing to the answer. So I would be summing them up, and after that point, I would not be adding it. And how I would be doing it? So what I would be doing is the idea is such that first we would keep a value. Initially, the value of this would be 0 or 1 according to your belief. Okay, if it is 0, it should be less than k. If it is 1, it should be less than equal to. Let's take it more relatable. That is, let us keep it 1. So we would visit the first 4. 1 is less than 2. So we would keep here 4. We would add the value 4. Then we would improve over this. Then this is 2. So 5. 5 we would add it because 2 is less than equal to 2. So now we have it. So 5, 4 plus 5 is equals to 9. Okay. Now let's sum up one more on the again the next sample test case. So now if we do the in order traversal of this, the value would be the left and then the root and then the right itself. So we have the left part. So we will be passing 20. The left is not visited. So how would we visit the root itself? Then we go to this part. Then 8's left is not visited. So how would we visit 8? So now to visit 8, we would be going to 4. 4's left is visited. So now we would visit this. So 4 is now visited. So 4 left, 4 itself is visited, 4 left is visited, 4 right is not there. So now we would be going again to back 8. Now 8's left is visited. So now we would visit the 8 itself. So now 8 is visited. After itself is visited, we would go to the right part. So going on the right part, we have 12. Now to visit 12, we need to first visit the right left part of it. So we would be going to 10. So now we would be having 10. And then the left of 10 is not present. So 10 is complete. We would be going to 12. Now the left part is complete. So we would be having here 12. Now 12 is complete, left is complete, we have right. So now we would have 14 itself. Okay. Now 8's right, left and the root all are visited. So it coming to 20. So now we have the left part everything done. So we would be now visiting 20. And then the root is visited. So we would be moving to the right hand side, that is 22 itself. Now what we could do is we would take the value 3. So 3, we would be taking these all elements. So now what we would be doing is we would be passing with the reference. That is, this value won't be copied, okay? With pass by value, pass by reference. Please read about this if you want to. Okay, so now what we would do is if the value of C is less than equal to the value K, we would just add this. Now let us move to the coding part and you would understand it much better. Now let us start this. So what we would do is we would design an in order. So that would return me an int value and then we would have node star the root itself. And then we would have int k and then we would have and the value c itself. So we would say that if the root equals to the value null, then we would simply return 0. That is, it would contribute 0 to the value. Then we would say we would initialize the answer is equals to 0. Okay. And then we would first add the value of in order of root's left value. So root, first we would visit the roots left with k being the same and c being the same. And then we would go down. Now, if after visiting the left side, if c is less than equal to the value k, okay, then only we would add the value. First, we would increment the value of c, and then we would add the value answer plus is equals to root dash data itself. After this is done, we would add the value of in order of root dash right itself with the value of k and c. Okay, and then after this, we would return the value of answer itself. Okay, now what we would do is we would initialize in c is equals to 1, and then we would return the value of int and then root comma k comma c itself. Okay, so we would pass this c to the in order traversal. This is the root, which if it is the null value, it would contribute 0. If it is, we would initializing answer 0. First, we are taking contribution from the left part. After that, we are visiting the root, and then we are again visiting the right part. Okay, just see, compile and run and see if it is working or not. And yes, it is working for the sample test case. Let us try to submit this and see if we can get an AC or not. And yes, we got an AC. So now we have optimized the space complexity at this point. Now, if you were here till this point of the solution, consider liking the video and commenting on the video for the better reach of this video. Thank you and have a nice day.